Okay, hi. Good morning, everyone. So it's week 9. Today we'll be talking about amortization. Okay, so let's see. All right, so I started recording. First, administrative matters. Midterm results are out. It was announced I think 2 days back. So please do check your grades and ensure that the marks have been tallied correctly. So I think Prof has specific instructions about checking the midterm solutions and look at the marking rubrics. And if you have any queries, do email Prof. And I believe the deadline should be by tomorrow, 15 March by 2 p.m. But do check the announcement again because this is what I took like last night. Okay, so I don't know how you guys are feeling about the midterms, but well, like regardless of what happens, I guess there's still a few more weeks to catch up in case like you feel that you could have done better. Okay, so which also brings me to like the next part about where are we in 3230. Okay, so this is the table of content for today's tutorial. We're gonna talk about amortization and the accounting method and potential method. Okay, so first of all, like where are we exactly in 3230? Okay, to give you a good idea of like how far you have gone and how far more will you go. So these are the first 6 weeks that you studied, right? And you just recently had your midterms. Okay, so lecture-wise, I believe in week 8 last week you have amortization, and this week should be talking about dynamic programming. Okay, and the tutorial today is well based on like amortization, which was last week's. Okay, so after this week, there are actually just 3 more lectures, one on this topic called greedy algorithms and 2 lectures on this topic called NP-completeness. So I personally feel that, these 3 are in the okay side, like maybe comparable to the previous one, or maybe slightly easier to some people. Okay, it's less mathy, I think, compared to the previous ones. So that might be good news to some people. It's more of an algorithm design kind of thing. Okay, and greedy typically tends to be intuitive to some people. NP-completeness, on the other hand, tends to be difficult. Okay, so I do foresee like a lot of people being confused and needing some more help in these little topics. And I highly recommend you to like attend the lectures, even though you maybe like have not caught up on these 3 lectures. Like in week 11, just attend the lecture anyway, because I think it should be pretty independent. Okay, so just letting you know like how much more we need to cover before we can start preparing for finals. Okay, there are no lectures on week 13 because I believe it's the NUS Wellbeing Day or something like that. Okay, so yeah, so this is where we are in 3230. So with that, let's begin today's topic proper on amortization. Okay, let's talk a little bit about amortization and motivating it, right? Because in amortization, what we want to do is that we want to analyze the sequence of operations, okay, on data structure. And typically, how you reason about the running time is by taking the worst case running time of each operation. But the thing is, right, by doing this, you might be overcounting, right? What if some operation actually take way less cost, right? So for example, here the operations, just because the second operation takes so much cost, right? You don't want to have a case where like you upper bound. Sure, it's correct that you upper bound everything by that amount, right? So if you consider that, that's fine. That's an upper bound, but then it's not always tight, right? So you might be overcounting. So we want to avoid this kind of like overcounting scenario, and that's what we are here for amortization. Okay, so amortization is really like kind of trying to change your perspective about how to count the cost of each operation. Okay, so common techniques involve aggregate method, accounting method, and potential method. Accounting method, typically some people refer to the banker method because it involves some form of money. Potential method is a physicist because there's the potential function being defined. We'll see that in a while. Okay, so the goal of amortization is really to give a guarantee of average performance of each operation over all the operations so far. Okay, so it's on the operation so far. So at every point in time, you are able to say like, okay, up to this point, what is the average performance? Okay, and take note a little subtle difference here. There is this notion of average case analysis. And average case analysis is kind of like over all the possible random inputs, like on average, what should the result be? That is average case analysis. Amortization, on the other hand, has no randomness. It really just simply averages over what happened so far, over the total cost of all operations so far. Okay, so just keep this in mind. Okay, it's okay if you don't fully understand this yet. You just keep this in mind that it's different. So for today's tutorial, we won't be discussing aggregate method. Personally, I think that it's not as flexible as the other two. Okay, so we'll be talking primarily about accounting and potential method. All right, so let's talk a little bit about accounting method. Okay, so the analogy is kind of like living expenses. Okay, so let's say you have a daily allowance of $15. Okay, let's say. Then every day, maybe you need to spend a bit, maybe for your food or for other needs, right? So you set aside some money every day just to spend on this food or your other needs. Let's say $5, right? So at the end of the month, right, you have to pay rent for, let's say, $120. And I'm aware rent is not this cheap. Okay, let's just say, for example. But the thing is, this is expensive. It's more than your daily allowance, right? Because if you have a daily allowance for that day, definitely that daily allowance is not enough to pay for the entire rent. Okay, so but the thing is, you have set aside some money every day for the past, like, before the end of the month. So what you do is you use the money that you set aside in order to pay for that rent. Now, in a sense, this rent of $120 is cheap, like double quote cheap, because your savings paid for it. It's cheap with respect to like what you have to spend for the day out of the daily allowance. Like with respect to the daily allowance, it's kind of cheap because your savings paid for it. It doesn't take anything from today's daily allowance. Okay, so this is kind of like, I guess it's very intuitive, very logical. I hope like you save some money ahead of time so that you save for a rainy day. Okay, that is really accounting method in a nutshell. Okay, so the idea here is really to impose, with respect to like algorithm analysis, it's to impose an extra charge on inexpensive operations. Okay, so operations that are supposedly not that expensive, you kind of give it some extra charge. So you use it to pay for a later expensive operation. Okay, so formally, like we try to charge the IF operation a fictitious amortized cost, right? Where $1 is kind of like 1 unit of time. And the analogy here is your daily allowance, right? So your cost for the IF day is, amortized cost for the IF day is $15 in the example just now. Okay, this is, you charge a bit more extra on supposedly inexpensive operations. So it'll be used in two ways, right? So you have to immediately pay a portion of that for the true actual cost, right? Let's say the true cost was actually your daily food. Every day you have to spend $5, right? But this $5 is forked from like the amortized cost from the daily allowance. And then the remaining one, you kind of like try to defer it by storing in the bank. So this is the money you set aside. Okay, so when the expensive operation come, you try to use money from the bank instead. And the analogy is paying the rent with savings. Okay, so let's formalize it with like example. Okay, so hopefully this example will make it clearer. So let's say like, you know, your bank contains no money, like here in the piggy bank or the froggy bank, it doesn't contain any money. So well, you know, you bought chicken rice, let's say for $10, right? So you have a daily allowance of $15 and you paid for chicken rice that day $10. So because of that, the money you have in the bank, you have $5 that goes to the bank is $5. So you store it in the bank over here, the little on the bottom left. On the second day, same thing. You try another food that also costs you $10. The actual cost is also $10. You get $5 extra, right, based on the daily allowance, and that also goes to the bank. So 5 plus 5 is 10. And let's say, you know, like this is just to emphasize the actual cost might be different for different operations. So in day 3, maybe you only bought groceries for $5, right? And based on the daily allowance of $15, you have extra $10. 15 minus 5 is $10, right? So that also goes to the bank, that's $20. And so on until like many days. Let's say after like this many sequence, after of this many sequence of going to the bank, storing to the bank, you have $150 in the bank. No need to care about how it came from. Just say like on this particular day, there are $150 in the bank. Okay. So, well, let's say on the 31st day of the month, right, the rent payment comes. You need to pay $120 on top of your like daily $10 needs. So with that in mind, like this $120, definitely your $15 daily allowance, your daily allowance cannot cover this very expensive rent payment. So what you do is you take it from the bank. use the saved up money, right? Have 150 minus 120, so you are left $30 in the bank. And again, like this now, this $120 is kind of cheap compared to this daily allowance of $15 because you in the past have paid for it in a sense. Okay, so you focus on what you have to pay for today, which is the $10. Okay, and well, 15 minus 10, like usual, is going $5 in the bank, and that stores an additional $5 to the bank. Okay, so to compute the total cost, right? Compute total cost. Well, suppose like you sum over all the actual costs and sum over all the amortized costs, and what you need, right? What you need is to ensure that the total actual cost is always bounded by the total amortized cost. So the one that you have, the daily allowance, right, is always higher. In a sense, this means the bank never goes negative. You never have to borrow from some other people. You are self-reliant. Okay, so the bank never goes negative. And so like why do we care about this inequality, right? So if you say that the total actual cost is upper bounded by the total amortized cost, let's say, right, you're able to bound the total amortized cost. Let's say it's bounded by ON, right? Then because the total actual cost is actually less than that total amortized cost, it has to follow the same bound. Because remember, like, let's say this is ON, right? Then, well, this is less than equals to like some constant CN, let's say, right? And if this holds, then this must also hold. Okay, so the goal of amortized analysis, why we care about this total amortized cost, is for us to define a way, right, such that this amortized cost, we have a bound on it. Like we can say that maybe the total is ON. The total is ON, therefore the total of the actual one, of the one that we really care about, the actual one, is also ON. Okay, so is that clear? Like anyone confused? Like, can you give me a thumbs up if that's okay? Okay, if it's not okay, do let me know. Like give me a cross and like maybe like chat me or something. Okay, so okay. So I think you're confused. Okay, so you're confused a bit. So any part that you want to be specific about? Okay, so a private message. What is this extra charge? Okay, so okay, so the question is, so the student is confused, like what is this extra charge that a process takes? Okay, so it's kind of like you kind of like imagine, right, that, so let's say this particular, you see this particular diagram, you kind of imagine it like, so the actual cost that you have to spend for the data structure, right? Like maybe adding something to the queue. Let's say it only takes one unit. Think of it as like, so for that 1 unit, so that for the purpose of analysis, what you do is that for that single 1 unit, you ahead of time, you say like, oh, actually, this guy is going to take 3 units. Like you and imagine that this particular operation takes 3 units instead of 1 unit, right? And then once the time comes, right, like okay, this diagram is not that okay. Let me redraw this. So let's say like the actual one looks like this, right? So let's say if you say that for every operation in the beginning, you impose like 3 units of charge. Like you imagine that instead the actual one is 1 unit. Sorry, the actual one is actually 1 unit, 1 unit of time, let's say, to enqueue maybe to the data structure. But you imagine that you overcount a bit. You overcount a bit for everything, right? You overcount a bit for everything. And then for this particular guy, once the expensive true operation comes, you make use of all this extra charge you put in the beginning to pay for whatever like this expensive operation is, so that it seems like you have already paid for it. It's kind of like, think of it as like redistributing the cost to cheaper operations. So this expensive operation, you kind of like try to distribute it to something cheap. so that when the expensive operation comes, it's kind of paid for already. Does this help clarify a bit? Yes, yes. So this incur an extra charge is kind of like trying to spread out the time units to other time units. Yes, that's right. One subtle thing I want to mention is that maybe like for the purpose of analysis, it's okay to have excess money in the bank. So like, even though I say redistribute, right? Like maybe you introduce like some additional cost that never existed, and that's fine, right? As long as you don't introduce too much. Okay, so it's okay to have excess money in the bank in a sense. Okay, so okay, thanks for checking. So let's go on to the first question, like some true false, some basic concept of amortization. So there are these three statements. Okay, so let me give you like maybe 2 to 3 minutes to fill in archipelago. Okay, so just to ensure that you're following, like which of the following is false. So let's resume at 11:20. Okay, and if you have any further questions, do let me know. Okay. I should have added an option. Like, I don't understand. Keep forgetting to add that option. Let's see. Let's see. Okay, so I think most of you should have filled in. Okay, so I've seen like around 16 participants. I think that's a good amount. So let me go on. Okay, so let me go on. So which of the following statement is false? Let's go through it one by one and like why some of them are true and why some of them are false. So option A is true. Okay, so the amortized cost for insert in dynamic tables is indeed like T01. Okay, and why is that? Because what you can do, right, for dynamic tables, so we call dynamic tables is that when the table is full, you double it and then you copy things over. Okay, so the reason it's okay is because you can imagine you charge $3, charge an amortized cost of $3 for every single insert operation. Okay, $1 for the insert, for the actual insertion, this is the true cost, and $2 goes to the bank. So okay, let's say, right, we just doubled the table. Okay, so we have finished doubling the table. This is the state of our data structure. I have 4 elements and 8 empty spaces. So every new element, right? If we insert 4 more elements, imagine like each of these element is associated to $2, right? So $2 in the bank, $2 for every single of this new element. Okay, so it costs $1 for the actual insert, and then we store $2 in the bank. So these $2 are in the bank. So the next time we insert something, right, we have to double. We have to double. And after doubling, we have to copy elements over. Okay, we have to copy elements over, but copying that element will cost something. Like for you to move from let's say this array A to array B, you need some cost to move things over, right? So how do you pay for that cost? That cost is paid for by the bank. So the first two elements, by copying, you use the $2 that you already charged ahead of time. Okay. Then the next two elements, you copy over by using also this $2 that you charge ahead of time, and so on. Okay. So, and so on. So now for you to insert a new element, well, the same thing, do the actual insertion, and now you have $2 in the bank again for this element. Okay. Here, I want to ignore the cost of allocation and deleting elements. Like these elements are, let's say, deleted, right? And this table has to be allocated. For simplicity, I ignore that cost, right? But you can also charge a bit more so that you can account for those charges. So again, like what I'm trying to demo here, right, is that for every single insert, you only need to imagine that you charge $3 for every single operation. So imagine that you charge just $3, which is theta 1, so that, like, for simple insertion, it's clear, it's gonna be O1. But for the expensive insertion, where you have to double the table and copy things over, you can imagine that most of the cost of transferring element has been paid for in the past. So that you can imagine that particular insertion that was supposed to be expensive is actually just also $3, because the cost, all the costs are absorbed by everything in the past. Okay, so hopefully that's clear, but if it's not, do PM me again and just stop me. Okay, so option C, right? So jumping to option C, which is also true, hinting for what's the one that's false. Okay, so well, C is true because this is what I mentioned earlier. The bank, right, must never go negative. Okay, so the total amortized cost must be larger than the sum of actual cost. This is just something that we want for in order to analysis to work. Okay, so this is, you know, just I don't know how much more to explain. It's just something that we want in order for the analysis to work. Okay, so in particular, like this particular slide, total actual cost is bounded by total amortized cost is the relevant slide that I wanted to show. Okay, so option B is false. Why is it so? Because recall just now, right? We have the insertion example. Our amortized cost for the operation is $3. This is what I assigned to it. Okay, well, I assigned to it, but the actual cost actually more than $3. Why? Because when you try to insert, you have to double and copy things. The actual cost, actually, you have to do some copying, right? Some copying of 8 elements, and then do the actual insertion. So maybe something like $9 here. Okay, so amortized cost, what the takeaway for this question is that a single amortized cost, right, might not necessarily be higher than the single true cost of that corresponding operation. But what's important is that if you sum over everything, if you sum over all the amortized costs, it should be an upper bound on the sum of the actual costs. Okay, so I hope that's I hope I said that clearly. Okay, so there's a subtle difference. So a single operation, the amortized cost, there's no guarantee that it'll be higher, it'll be lower, right? In particular, it'll be lower than the actual true cost because you want to use some money you have saved in the past in order to pay for that expensive actual cost. Okay, but the thing is, like, you want the total sum of everything of the total amortized cost to be a bound on the actual cost. Okay, so let me know if that's confusing, but I'll go on. Okay, so I think for the rest of the tutorial, oh wait, maybe I should mention something important here. Like here, this $3, right, it's kind of arbitrary. So typically this $3 amount, right, of the amortized cost is something you come up with yourself. This is what you're supposed to think about, like how much amortized cost should you assign for it. Okay, so yeah, just something I wanted to remark. Okay, so I think for the rest of the tutorial, I'll just go through it without asking Archipelago too much. Okay, so question 2 says consider a data structure that is based on a queue with these operations: NQ, DQ, delete, and add. Okay, so let's go through it. So 4 operations. NQ is pretty simple. If you NQ one item, just NQ one item, right? If you wanna add an array of items, right? Let's say add 2, 4, 6, 8. You're adding everything to the array. Okay. Delete 3 elements. Just says like, oh, DQ 3 times. Essentially. and then a DQ is just like, DQ one element. Okay, so 4 operations, simple and Q, like a batch adding, DQ some elements, and DQ one element. Okay, so these 4 data operations, the claim is that NQ, DQ, and delete K runs its amortized O1 time. Take note, it's amortized O1 time, and adding the entire array runs its amortized O the size of A time. Okay, so use accounting method to prove these time complexities. Okay, and to use accounting method, typically what you have to do, you have to state the charge. Like what I said earlier, you have to charge $3 for a particular operation. But this time it's flexible. You can like charge different amount, like depending on like your needs, kind of. Okay, so let's see. So maybe I want to mention here, right? Like NQ and DQ should be straightforward. You think it's normally it's O1 time. Adding A elements is OA time. That should be straightforward. But delete K elements is what's interesting to analyze here. Because if you delete like many elements, right? By right, typically delete many elements should be like O that many elements time. But we are claiming here in the amortized sense, right? It's O1 time. Okay, so let's see. So I just want you to like digest the question first. This question is going to be used for question 3 as well. So if you have any, can you give me a thumbs up if you understand the question? If you don't, like, please ask. Okay. Only 3 thumbs up. Is it because the rest is not understanding or maybe like not present? I think that's fine, but okay, never mind. So for those like maybe not sure, I'll wait for like maybe 20 more seconds and see if you have any questions about this, or if you want me to repeat, sure, like the operations, just ask me to repeat. Okay. See nothing so far. So I think I'll go on. Okay. So again, as I said earlier, right? Delete is where things get interesting. A naive analysis of deleting K elements should take OK time. But we now want amortized O1 time. So how do we do it? Again, the idea is always similar. You pre-charge other operations to pay in advance for deletion. Okay. So what you can do is that for an NQ operation, you charge $2, right? $1 is for the actual insertion and $1 goes to the bank. In particular, this $1 will be used for a future DQ for you to like pop it out of the queue. Okay, so adding A elements, adding the array A, right? You charge $2 times the number of elements, right? Same thing as before, because you can think of adding like the size of A elements as like multiple NQs. So each of them is charged $2, $1 for the actual insertion, and then $1 in the bank for future DQ. Okay, so now deleting is simple because all the deletes, right? You can charge nothing actually. You can charge $0 because you can argue that the actual cost is already paid for already by that same insertion in the past. Because when you delete K elements, each of them have $1 associated with it in the bank, right? Each of them already have the associated $1 in the bank, and that will be used to pay for the actual cost. Okay, so in a sense, like someone in the past has paid for in advance for you to be DQ'd. And simple enough for DQ, for a normal DQ, well, that's also $0 because it's been paid for already. So like notice here, I have K elements, but never mind the K elements, those K elements have been paid for it to DQ. So that's the essence of this question, to redistribute the cost so that the delete becomes cheap. Deleting multi-element is cheap. Okay. So one thing to argue, right? So it seems like, wow, too good to be true, like so easy to argue. Like just again, take note, does the bank ever go negative? And this is something important that you should check, right? Because if the bank ever goes negative, the analysis doesn't hold. I can talk more about it later, but just keep this in mind first. Okay, so Does the bank ever go negative? Because after each insertion of element, you have $1 associated to each element in the queue. So that when we dequeue that element, just use that $1 in the bank. Because like in a sense, right, the information about the money stored in the queue is equals to the number of elements in the queue. So when we dequeue, it's always enough. There's always enough money in the bank. Okay. So to summarize these operations, right? The actual cost is this much: $1, $8, $1, K dollars. But you do amortize cost. You do an amortized cost by assigning each of them like different amortized cost. So that you can say that NQ is cost $2. The amortized is $2, which is 01. DQ is also $0 and delete is also $0. So that's kind of like 01. Adding A elements is 2A. So it runs in amortized OA time. And then like this is the effect on the bank. Like this operations, like what does it do to the bank? Like this one plus 1, this one plus A, this one minus 1, this one minus K. I'll keep it in this slide for a bit. Like I'll just again ask like thumbs up if you are okay with this, and if not, please stop me, because the next part is gonna be like also on the same question but on potential method. Yeah, so okay, so there's a question in the chat, like you are unsure how to come up with the charge, right? So okay, so I think coming up with a charge is really question dependent. So for the previous question, it was $3, and now we say that it's $2. So coming up with a charge is really indeed like what you are tasked to do. Typically, you have to think about like, what should the other operations be? What should the other expensive operations be? So here, right, our expensive operation so-called is deleting K elements, right? So deleting K elements, if you think about it, right, to delete K elements, they must have existed in the queue first. The K elements must exist in the queue first. So those elements that are in the queue first must have been inserted, right? So let me say again. So delete, when you do delete K, those K elements must have been enqueued first. So in a sense, like you can try think of it as like, oh, how do I shift the cost over from delete K to enqueue? Like shift cost. So notice how every enqueue, right? Every DQ only costs like $1 in a sense, 1 unit to pop out of the queue. So you can say like, okay, can I try to make it free? Every DQ, can I try to make it free, like has been paid for? So for this K elements, you kind of like move the $1 over to NQ. So every single element that was DQ'd, the $1 to pay for it is moved to the NQ. Maybe I apologize if it's still a bit confusing, but I think this is really like where we should try to practice more, have more exposure to different kind of questions, because the amortized cost here is really something that you have to try to come up with by considering everything, like all these operations, which one are the expensive ones, how can you shift the cost around a bit. If you want to say the amortized here cost is $3 here, technically it's fine. You are just slightly overcharging. Sometimes that makes analysis simpler, okay? But it's totally fine if you want to keep it $3. This $2 here, I'm being exact, but this like amortized cost in general, you can assign anything. Okay, you can assign anything you want. You can even say $100. That's fine. I mean, $100 is one time, but that's a bit like overkill for this analysis. But it works. It will still work. Okay. Okay, so you get it. All right, great. So let's go on. Exactly. I say here, it's okay if I decide to overcharge. Like if let's say amortized cost is $5, if it makes argument easier. Okay. So that kind of like wraps up accounting method. I'm gonna talk about potential method for, is it always better to have a very, okay, so the question in the chat, private chat, is it always better to have very large amortized costs? So I would say always better. Typically, I say it's easier to argue about things, but you also have to take note, like when you say larger, typically larger has to be like by a constant amount lah. Don't charge by like, if I have n elements, like let's say I have n operations. Don't charge n dollars, because n dollars is like dependent on the on something, right? This is gonna be like O n in a sense. So, but let's say if you charge $100 here, I think it's fine, right? It looks large relatively, but it's still a constant amount. Still a constant amount. And typically it makes analysis for some questions easier. It's not that evident in this example, but I think in the past I've seen questions where it's easier if you just like charge many in advance. That's a good starting point also, by the way. Like if you're not sure, just overcharge first and then see how the analysis goes. It's a lot of trial and error. You probably won't get it in your first time. So trial and error. Okay. So potential method, let's go. So potential method, I just want to say in advance, right? Potential method is another technique. Some people will find it intuitive. I personally don't find it intuitive at first, but later on, like it's quite similar to accounting method actually, but it's okay if you don't see the similarities. So now shift your mind a bit, like forget about accounting method. Potential method is like a new method, a separate method. So in potential method, instead of paying in advance by storing money in the bank, you kind of like pay in advance by building up some potential. Okay, so this might not be clear. So there's this potential function phi. Phi is the potential function associated with the algorithm or data structure. And I want to emphasize, right, the phi here is something you have to cleverly define yourself. So again, this is by experience, you have to like figure out what should be the amount, should be the function, and you have to trial and error basically. Okay, so phi of I is the potential at the end of the IF operation. So after you are done with the IF operation, that's the potential. We define the potential difference. I think in the lecture, Prof didn't really use this notation, but I hope you should be familiar by now, like delta phi of I means like difference between something and something. Here, delta phi of I is the potential difference going from the I minus 1 to the IF operation. Let's see with an example. Okay, let's say like, this is how the potential function goes. Like it kind of like climbs up, goes down, climbs up. Okay, so at the 9th operation, okay, at the 9th operation, wait, let me see. So 2 minus 10. Okay, so if I want to interest the potential difference at the end of the 9th operation, what I do is I compare with the 8th operation. So the 2 here comes from the 9th operation, and the 10 here comes from the 8th operation. The potential difference is take 2, what's the difference to 10? So in a sense, like this delta of phi of 9 is -8 because the potential difference is -8. It kind of drops potential by 8. Then delta of phi of 10 is increasing the potential from 2 to 3. So this is +1. So there's the potential difference. So recall, like I want you again to distinguish phi of I is the potential, delta phi of I is the potential difference. Okay, so it's okay if everything is not so clear yet, like why are we doing all this notion? Okay, so here's an analogy which I found from like Stack Overflow. It's hard to find a good analogy for potential method, and I didn't think that this still clicks that much, but I'll try. Maybe it clicks to some of you. So analogy is like water tank, right? So when you open the faucet in like a water tank here, right, you have a nice water pressure if you have a lot of water inside it. It's high potential if there's a lot of water. So, but if there's empty, then there's like no pressure. Okay, so you need to slowly refill. If you refill the water inside that water tank, it kind of like build up more pressure. It's kind of like building up potential energy. Okay, so if some of you are physicists here and then you find this very strange, please bear with me. Okay, so potential function here, right? Let's say I define it as the water in the water tank itself. So as you fill in more water, the potential increases, right? It kind of builds it up. And if you draw water, right, there'll be some nice water pressure for you to get the water. But over time, as you do the operation of taking away water, well, potential will also decrease because the water in the water tank itself decreases. Okay, so what's the relation with amortization, right? So in a sense, like if you draw a lot of water, that's the expensive operation, but it becomes cheap. It becomes cheap because the potential here will help push it out for you. Okay, so drawing a lot of water is supposed to be expensive, but then because of the potential that you build up, it will kind of like make it cheap. in a sense, right, this is the similarity of accounting method. You store up things in advance, you store up energy in this case, so that you pay for the expensive operation. Okay, so it's okay if it doesn't click yet here. I agree potential method can be confusing. Okay, so take some time to understand it later. But let me just go on for now. Again, I want you to remember phi is the potential function. Phi of I is the potential at the end of the I of operation, and delta phi of I is the potential difference. Okay, take the current point in time minus the potential in the previous point in time. Okay, so now I want to show why potential method works. I think Prof kind of like skimmed through the calculation a bit in lecture. Okay, so in potential method, amortized cost is different, defined differently, right? I want to show that the sum of amortized cost is greater than equals to the sum of actual costs. This is what we had in question 1, right? I want the sum of amortized cost to be higher than sum of actual cost. But a single CI versus a single TI, you know, like we don't really know what their relation is. What we care about is that their sum, right, must be greater than equals to. So we can conclude the same thing as before, right? If this is ON, then this is ON as well. Same as before. Okay, so let's see how we do it. Okay, now in potential method, amortized cost has a different definition. Amortized cost is defined as the actual cost plus the potential difference. Okay, so again, throw away your understanding of accounting method for now. In potential method, amortized cost is just by definition this thing. It's not like charging money, like, oh, in accounting method, it's like charging money, and that's the amount of amortized cost. In potential method, this is the definition of amortized cost. So it's like a different realm entirely. Okay, but this definition, how do I make sense of it, right? So basically, for the cheap operations, right? If this is cheap, let's say this is like 1, right? We want delta phi of I to be also positive and small. Like let's say this is maybe 2, like small, so that if you add them up, this is 3. This is the amortized cost is $3. Okay, I shouldn't say dollars because they'll confuse you with accounting method. Okay, but let's say, right, the TI is large and this is the expensive operation. This is 100. Let's say this is 100 or maybe 1,000, right? I want this delta phi of I to be also very negative, like let's say negative 999, so that if you add this up together, it becomes cheap. So this potential difference is the one that kind of like keeps track of the potential. Okay, it keeps track of the potential such that when you do the expensive operation, you suddenly drop to a very low potential. You drop to a very low potential and make use of the potential you have built so far in order to pay for this expensive operation. Okay, so the goal here is to, at the end of the day, I want the amortized cost to be small, regardless of what TI is. That's the goal of potential methods. Okay, so it's 11:45. I hope I can finish like at least the next question on time. But I want to take this part slow because I understand potential method is confusing potentially. That's a accidental pun, but okay. So additionally, one condition I did not mention so far is that the potential, typically we define phi of 0. Basically, at the start of the operation, we haven't done anything yet. The potential should be 0, and every potential should be non-negative. Okay, so it should be non-negative. So basically, the graph of the potential function, it should always be like in this region somewhere. It should never be in the negative region. Okay, so this is the potential method definition. At this point, any questions? Like, does anyone need help with this part? Like, can you give me a thumbs up if you roughly understand? If not, again, stop me again. Like, no shame in asking. Okay. I'll say it one more time. In potential method, this is the definition of amortized cost. It's defined as the actual cost plus the potential difference to reach that IF operation. Okay, and our goal is to make sure that the amortized cost will end up being small. Okay, so warning, math ahead. So I want to like show this part now. Why is it the actual sum of amortized cost is sum of actual cost? And I think because Prof kind of like briefly only said it in lecture. So this is by, let's say, right, we sum up the amortized cost. CI is the amortized cost. And by definition, it is TI plus the potential difference. This is by definition. Okay, so this thing is equals to Tn plus this thing. This is like for I equals to n, for I equals to n minus 1, and so on until I equals to 1. This is just me unrolling the loop, unrolling the sums. Okay. The neat thing about this analysis, and I think Prof just briefly mentioned, is it telescopes. Telescopes meaning that this cancels off like this in this manner. So it cancels off like that. It leaves two terms. This thing, sorry, it leaves two terms in terms of phi. And all of these things are untouched, but everything else got cancelled away. Okay, so to sum up over Ti, we sum up over Ti, and then there's this remaining not cancelled like phi of n and minus phi of 0. Okay. At this point, this is just like by using definition, unrolling the loop, and then cancelling the math. Okay, so taken from the previous slide, this is what we have so far. Sum of actual cost, sum of amortized cost on the left-hand side is actually equals to the sum of amortized costs plus these two terms. Okay, so we know that phi of 0 is 0, right? This is the condition that makes it convenient. This is 0, so this is like just minus 0. And then we say that phi of I for any I is greater than equals 0, right? So it means that this thing is greater than equals 0, and that gives this inequality here, because that means that the left-hand side is actually Ti plus something non-negative plus something more, and that gives us this. So we have that the sum of amortized cost, this sum of amortized cost, is greater than equals to the sum of the actual cost. Okay. So this is the derivation. It's okay if you don't understand this derivation yet. Okay. I just want to convince you why potential method works. Okay. So this is why potential method should work. And then, well, same thing as before. If we know that the sum of amortized cost is, let's say, like bounded by some function fn, then, well, something that's even smaller should also be bounded by fn. That's the point of this argument. Okay. So again, like here I said earlier, if we bound the total amortized cost, we bound the total actual cost for free. All right. So the recipe here, right? Like again, potential method, I want to emphasize that the phi here, you have to define yourself. Okay. And how do you define it yourself? Here's kind of like double quote recipe. You should see how to define it in a way such that the potential difference is negative for the costly operation, right? And you try to view the costly operation and see if there's some quantity that is decreasing. Okay, see if there's some quantity that's decreasing during the operation. And I hope it'll be clear in the next question. Okay, so to define phi, you try to find for the costly operation what is decreasing. Okay, so it's 11:50. I think I'm gonna run out of time, so apologies. But when to use accounting and when to use potential, I just want to say that, you know, like depends on, we'll usually tell you what to use. Okay, choose whichever one you find more intuitive. Okay, if they give you an option, whichever one is more intuitive. I find accounting method intuitive, more intuitive than potential. Okay, but some people might beg to differ. Okay, so okay, that's a whole lot of manual of potential method. I will demo with a question, but at this point, anyone have any questions? Okay, if not, I'll go on and talk about the same question as before, the fancy queue, but this time I'm going to use a potential method to analyze. Okay, so not going to fill in archipelago, so let's go on now. Okay, so remember, we want to define a potential function so that for costly operations, we try to nullify what is actually decreasing during deletion. Okay, so well, what's decreasing during deletion? Like the expensive operation we care about here is delete k elements. What's the thing that's decreasing? Obviously, it's the number of elements, right? Like if you take these k elements in the queue, then the number of elements is what's decreasing. So we define, again, I emphasize this phi of I is defined because I observe that, hey, number of elements in the queue, they decrease after the K of, like after the expansive operation, or for all the delete operation, in fact. So this is how I define phi of I. So with this definition, let's argue what the amortized cost is for every single operation. Okay, so for enqueuing, the actual cost is 1. And then remember, the definition is actual cost plus potential difference. Potential difference, right? So the potential difference here is phi of I minus phi of I minus 1. And remember, like, because how we define it, the number of elements in the queue after the IF operation, it increases by 1, right? After adding 1 element, it increases by 1. So the amortized cost is 1 plus 1. Okay, so for DQ, it's the reverse process because the potential difference is taking away 1 element. So the potential difference is -1. The potential decreased by 1. So the amortized cost is 1 plus -1. 1 comes from the actual cost, so it's 0. Deleting K elements, where this is where we cared about it initially, we have K less elements, right? So the phi of I minus phi of I minus 1, the potential difference is minus K. You take away K elements. Okay, so actual cost is, amortized, I'm confused. So actual cost is K, the potential difference is minus K. So amortized cost, which is again defined by actual cost plus the potential difference, is K minus K, which is 0. Okay, so adding, same thing. I think I won't repeat myself again here. So what we have to argue is that it should fulfill like phi 0 equals 0 and phi of I is greater than equals 0. Phi of I is the number of elements after the IF operation, right? So in the beginning, we have an empty queue. So definitely it's 0. And we never have negative elements. We never have negative elements. So the number of elements never go negative. So it's never a negative value. So these two conditions are fulfilled. Okay. So I know I kind of like speed run that question, but is it okay? It's right now it's 11:54. I'm definitely over time. So what I'm gonna do, I'm gonna like wrap up the tutorial. Like I'm gonna share the slides, but I'm gonna go on to explain question 4 since this video is recorded for the cohort use. Okay, I just want to wrap up a bit. Again, I want to emphasize amortization is really about like trying to change the perspective, how to redistribute the cost of the operation. So again, don't be too hung up on the recipe. Try to be creative. As long as it makes sense, I think should be fine. Okay, so tutorial and lecture examples are actually very simple examples. You might not see the full capabilities yet. It seems like too easy to be true, right? So there are more difficult examples to convince like the power of amortization. Examples explore here. I'm going to share some things in my supplementary slides, but there are several other neat examples you can try and see if you're interested for further examples. And in case like this is confusing to you, like still confusing what amortized analysis is about, there's this lecture by MIT, Massachusetts Institute of Technology. So it might clarify some things, but take note, they have one additional method which we don't typically recognize in 3230. So just be careful. Okay, so I'm just going to share my slides now in the chat. And after that, I will resume with like explaining question 4 because okay, there's a question in the chat. I'm going to get back to you soon. Okay, so I'm going to share the slides here. And I put here a feedback form in case like you want to tell me something and you want to do it anonymously. So I'm just going to keep it open for the entire sem. Okay, so thanks a lot for coming. We have several other more tutorials, like I think about 4 more tutorials to go through. So feedback is appreciated. Okay, so going back to a question in a private message in the chat, there's a question saying like by never have negative element, is it never have negative index? So remember the queue, right? The queue here, it's kind of like what happens if you have a queue in a programming language. What happens if you do q.len? Q.len, can this ever return like -1, -2, -3? Like that's what I mean by never have negative elements, because it's either you have nothing in the queue, right? The potential method, the potential I define is number of elements in the queue after the IF operation, right? So the elements in the queue is either 0 or it has something. So it's positive if it has something. but it's never negative because it doesn't make sense. What does it mean for a Q to have negative elements? I'm not too sure if that's what you mean by negative index. Okay. Okay. So I'm gonna maybe like wait if you have any more questions about the current question. If not, then I'll go to question 4. Okay, I'm really sorry for overtiming. I think maybe I explained a bit too slowly, not too sure. Okay. Okay, question 4. Dynamic table. Okay. The dynamic table here in this example is delete only operation. Okay, so we have the idea here is that we start with a full table, right? So the pseudocode is here for your usage, but I want to like the idea here overall is to start with a full table, and once the number of elements is half the elements it can hold, we try to halve it. Okay, we try to halve the table. So one thing to take note for this particular example, we do not call any other operation on T. So we don't mix and match operations. We care only about deletion starting from a full table. Okay, so we show that by amortized analysis, this is O1 using the potential method. Again, we have to state the potential function. So again, let's recall like potential method, we have to define our potential function. And how do we define it? Let's see, right? So there are two possibilities when you delete. Table doesn't shrink, just delete. So just take away the element, just take away one element. This is a cheap operation, right? The second case is when the table shrinks. When you delete this element, it becomes half the size of the table. Okay, so then you halve the table and becomes like this. So this is expensive because you have to copy things over to the new shrunk table. Okay. So you want to look for a decreasing quantity during the expensive operation. So what is the potential function here? Okay, so again, observe what is decreasing during this thing. You might be tempted to say like, oh, is it also the number of elements? Sure, the number of elements, number of elements decrease, but what about the size of the table, right? The size of the table meaning like how many elements can it hold? In case it's, I just want to say here first, in case it's confusing, size here refers to like how many elements can it hold, where, you know, like the actual elements it hold is lower than equals to the size. Okay, so you might think of, oh, the size decreases from 8, now it becomes 4. Okay, so sure, this is a potential function that's decreasing, but take note, phi of 0, we want it to be equal to 0. But then we start off with some non-empty table, meaning that we started off with 8. We started off with table that can hold 8 elements. So phi of 0 is kind of like, let's say 8, something that is greater than equals 0. So it doesn't quite fit our condition where phi 0 equals 0. Okay, so another way to define it is size of t minus n. So this is n. This is size of t minus n. What is this thing? So size of t minus n, if you look at it mathematically, it might not make sense, but this is actually the number of empty slots. How many slots are empty in the table? And verify it satisfies these two conditions. Why? Because the number of empty slots, you start off with a full table. So at the beginning, there should be 0 empty slot. But then for all the other operations, well, then it doesn't make sense to have a negative empty slot. Yeah, it's always like either full or there's some empty slot. Okay, so this potential function is our choice of potential function. So this is defining a new potential function in this manner. So let's now remember that in potential method, the amortized cost is the actual cost plus the potential difference. Okay, and let's now analyze the two cases, right? What's the cost of deletion in the two cases? So in this case, this is cheap, right? The first case is table doesn't shrink, is cheap, just delete. So the actual cost is just deleting one element. What's the potential difference? The potential difference, again, is the number of empty slots, right? And the number of empty slots increased by 1. So potential difference is 1. Okay, so the amortized cost here will be 1 plus 1, which is 2. Okay, so it means that for this easy case, our amortized cost is actually just 2. Okay, what about the expensive case, right? For the expensive case, let's study in this way. right? So for simplicity, I'll refer to n as the number of elements at the end, but it doesn't matter if you base it like here as well. But let's say I have n elements in the end. So previously, before deletion, right, this is n plus 1 elements in the table. Okay, so this operation is expensive because you have to copy things over. So what is the actual cost? Actual cost is n plus 1. Where does it come from? It comes from deletion of this thing and then copying the remaining things. Right? So it's n plus 1. What is the potential difference? The potential difference is 1 minus n, but this might not be clear. But if we use the definition, right? Remember, potential method is the number of empty slots. Before, the potential before it is the number of empty slots here, right? This is 2n minus n plus 1. 2n minus n plus 1. This is the potential before deletion, which is n minus 1. Okay, potential after deletion is 0, right? There's no empty slot. There's no empty slot in the queue. So this potential difference is 0, where 0 comes from the potential now, minus the potential difference before, which is n minus 1. Okay, to give you 1 minus n. Okay, so another way you can think of it is that, you know, this is initially we have n elements here and minus 1 empty slot, here. This is n minus 1. Okay, sorry, that might be confusing. I won't go that path. Okay, so follow this math carefully, and you should realize that the potential difference is 1 minus n. And the amortized cost is summing up the two things together, n plus 1 minus n, to get you 2. So the 1 plus 1 here becomes 2, and n and minus n cancels off to get amortized cost of 2. So maybe to like reconsolidate everything, the choice of our potential function is really so that the expensive operation gets nullified by the potential. So there is a huge drop in potential here. By this expensive operation, there's a huge drop in potential from like the number of empty slots from some value to 0. There's a huge drop in potential, and intuitively this drop in potential is what is used to pay for this expensive actual cost, okay, to become the amortized cost. So to summarize, this is the table to summarize everything. The case 1 of deletion is no shrinking, and to give you amortized cost of 2, and case 2 is shrinking, which also gives you an amortized cost of 2. Okay, so yeah, so that concludes the question 4. I hope that is like somewhat followable. It's okay if you're still confused. That's very normal for potential method, I think. If you want me to repeat anything, do let me know. Otherwise, this is like the end of the tutorial. I think I've said what I wanted to say. Again, sorry for being over time, and those watching the video, thanks for watching this far. Okay, so if you have any questions, do let me know. I'm just gonna stay back until like there are no more questions. Okay. Okay, so there's a question in the chat, like, are we supposed to find a potential method that will give the same amortized cost for inexpensive and expensive operations? So I suppose like you're referring to this thing, right? Like why they are both 2. So I suppose like it should result in the same thing, but in respect where it's constant, right? It's still both O1. So I don't see a problem if your choice of potential function makes it like 1 and 3, for example. Like it doesn't have to be strictly the same thing. But your potential function at the end of the day, you want to give it like a good guarantee of what it is. Like it's O1 for both. Like it's O1 for both. It's still constant. So of course you can define a potential function differently. If you define a potential function differently, and maybe, for example, right, I can't come up with an example right now. Maybe this ends up being still n, like I don't know, n over 2, and this becomes like 3. Then, well, it's different, and that is totally fine. But the thing is, you are not showing anything meaningful, because in this case, you show with your choice of not so well defined potential function, it becomes that one of the cases become expensive. It becomes ON. So you don't say anything meaningful about this particular operation. I want to emphasize that in this particular question, right, is that we only have one operation, which is delete. Just that the delete, right, has two cases. So I want to show delete is O1. And I do that by separating the two cases of delete that might be expensive and might be cheap. So in both cases, very conveniently, the answer becomes 2, okay, by our choice of potential function. But I think it's fine if your choice of potential function somehow gives this like maybe 5 and 3. Delete is still O1 because for the expensive case, delete is still O1 in the amortized sense because in the even for the expensive case, the amortized cost is just 3, the constant, and this one is 5. Does that answer the question? All right, great. Okay. All right, no problem.
Hi, sorry. Can I just ask, right? For like amortized analysis, right? Let's say we don't start with something nice. Let's say like, let's say for the dynamic table example, right? We start with like 0 elements in the table. In the lecture example. But what if we start with a number like 7?
Right. That's a good question, right? So amortized analysis really depends on the state of the initial data structure. Okay, so I think in that case, that really let me think. Yeah, so I think let's say for potential function, right? I think a good benchmark to go for is really like this. Wait, let me go where it's here. So where the potential of 0 is 0. So the initial state, let's say you have 7 elements, right? Maybe depending on your potential function, you can adjust it a bit, like maybe like add a -7 to it. It's a bit ugly. But I guess to like kind of like follow what we have in lecture or like the recipe for potential method, this is how we might approach it, I feel, right? To make sure that you start off with 0 potential and from there on you make forth the analysis. So it's kind of as if like the initial state is 0 elements, but that's a very good question. It's important what the initial state of the data structure is and try to adjust accordingly and see if I can imagine maybe for accounting method, right? Like maybe to delete those 7 elements. Like let's say I started with 7 elements, and then you want to delete. Let me see. Yeah, it's kind of tricky, but I think it's good that you raise it up. So let me think a bit more. So you have 7 elements in the queue. 7 elements in the queue. In a dynamic table, then maybe you want some operations. Like let's say adding, right, to charge some amount so that charge a bit more, like really overcharge for some operations to account for like the existence of prior elements. Maybe that will work. Yeah, but yeah, I'm sorry I didn't give a very good answer, but I hope that somewhat like gives you an idea of how to do it.
Yeah, I have an idea now. Okay. Thank you very much.
No problem. Yeah.
Thank you. Bye-bye.
Bye. Okay, so yeah, that's the end of the tutorial. Again, sorry for over timing. So yeah, I'll stop the recording. Thanks for watching.